Hello dear students, in this session let us study the concept of Picard's theorem. Okay, so this is nothing but the existence and uniqueness of first order differential equation. So we will study this concept today. The statement of the theorem says that we are considering a function f of x comma y. This is a real valued function. Okay, so this real valued function is continuous over a region. Here the considered region is a rectangle. Instead of just considering a real line, we are considering a rectangle. Okay, so this is a function f of x comma y. It is a real valued continuous function over a rectangle. So we are defining a function as r from mod x minus x naught is less than or equal to a and mod y minus y naught is less than or equal to b. This a and b are your intervals. X and x naught, y and y naught are the distance. So if I write a rectangle in this way, this is x-axis, this is y-axis, right? So initial point x naught to x. Similarly for y, I can consider 2 points, say initial is y naught and final is y. So distance between these two should be less than or equal to b, and distance between these two should be less than or equal to a. This is the condition, and we are considering a function such that the mod of f of x comma y is less than or equal to m. So you have already studied this concept in your real analysis. That is, if a function is less than or equal to m means it has both upper bound and lower bound, right? Or else you can say that your function is bounded function. So every bounded function is continuous. So thereby, since we have considered f is a continuous function, we can say that it is bounded. So from that I have written this relation. Okay, so this is for all x comma y belongs to R. So in the statement they have also given that suppose this f satisfies Lipskitz condition. So I have already given a reference theorem which says the condition which here I have mentioned that Lipskitz condition, right? I have given reference for this. You have observed that in your notes, I guess. So let us see what is that Lipskitz condition. A real valued continuous function f of x comma y on R, okay, is satisfying Lipskitz condition means if mod of f of x comma y1 minus f of x comma y2 is less than or equal to some k into mod of y1 minus y2. If this condition is true, then we can say that our function satisfies Lipskitz condition. Okay, for this here this k is nothing but Lipskitz constant. Let us see one example, that is how we are defining this condition. For that, I will consider the example as here my function is, I'm considering one function, say f of x comma y is equal to x y square. Okay. So this function is satisfying Lipschitz condition over the region mod x is less than or equal to 1 and mod y is less than or equal to 1. We have to show that this condition, this function is satisfying Lipschitz condition over the region mod x is less than or equal to 1 and mod y is less than or equal to 1. Let's see how we can prove that. So the condition is mod f of x comma y1 minus f of x comma y2 should be less than or equal to k into mod y1 minus y2, right? So now f of x comma y is given that xy square. So f of x comma y1 means it is x y1 square and f of x comma y2 means it is x y2 square, right? So mod f of x comma y1 minus f of x comma y2 will be equal to mod x y1 square minus x y2 square. If I split this modulus, I will get inequality. Since x is common here, I can write this as mod x into mod y1 square minus y2 square, right? So this is nothing but a square minus b square form. So I can write this as mod x into mod y1 minus y2 into mod y1 plus mod y2, right? So now from this condition, that is mod y is less than or equal to 1 and mod x is less than or equal to 1. So this whole thing is less than or equal to mod y1 minus y2 is as it is. Mod x is less than or equal to 1. So I can replace that with 1. Mod y1, mod y2 is nothing but 1 plus 1. 1 plus 1 is 2. So this is less than or equal to 2 into mod y1 minus y2. In the LHS side, I have mod f of x comma y1 minus f of x comma y2. This is less than or equal to 2 into mod y1 minus y2. This 2 is nothing but your k, which is nothing but Lipschitz constant. So this is nothing but Lipschitz condition. Okay. So what here in this theorem, what they are telling, if your f satisfies the Lipschitz condition on region R, then the successive approximations, they have given an approximation phi naught of x is equal to y naught and phi k plus 1 of x is equal to y naught plus integral over x naught to x f of t comma fk of t into dt, where this k varies from 0, 1, 2, 3, so on, right? And this approximation converges on interval. They have given the interval also. The given interval is I from mod x minus x naught is less than or equal to alpha, and this alpha is equal to minimum of a comma b by m. Here this m is some constant value. You can choose any value for that. So this is a solution to a solution phi of the initial value problem, and the initial values are y dash is equal to f of x comma y and y of x naught is equal to y naught on interval I. So as I have mentioned, these are successive approximations. Successive approximations are nothing but using a given approximation, you will find out one solution and you will use that solution to find out the next solution. So using previously obtained solution, you will find out the next solution, right? That is nothing but successive approximation method. So now I will prove this theorem using 5 steps. Okay, the first step is nothing but convergence of the sequence. So first I have to find out whether the sequence is convergent or not. Okay, because they have mentioned that if f satisfies Lipschitz condition, then there exists a successive approximation and that successive approximation is converging. They have mentioned that it is converging. So we have to prove that this phi k of t or phi k of x is a convergent sequence. Okay, then we have to prove that phi k plus 1 is also convergent. For that I will use mathematical induction method. Okay, first I have considered that phi k. I can represent phi k as phi naught plus phi 1 minus phi naught plus, you will get one more time, that is phi 2 minus phi 1, so on up to phi k minus 1. So this phi naught gets cancelled with this minus phi naught. Similarly phi 1 gets cancelled with next term, here you will get minus phi 1. So similarly you will get phi k itself. I can write this whole thing as phi naught plus summation p is equal to 1 to k phi p minus 1. I have called this as equation number 1. So if you just say this summation part, you can say that this summation part is nothing but sum of the infinite series. You have studied those things in your real analysis, right? So since this is a sum of infinite series, I can write this as phi naught plus summation p is equal to 1 to infinity phi p minus 1. So I have to prove that this phi k is convergent. So to prove that phi k is convergent, it is enough if we prove that this equation number 2 is a converging sequence, right? In order to prove this equation 2 is convergent, I should find out what is this phi p minus 1. So to find out this value, I will use the reference theorem. The reference theorem is nothing but your Lipschitz condition. You have a theorem before that, right? Using this theorem, I can further write it as mod phi 1 of x minus phi naught of x is less than or equal to m into mod x minus x naught. I will call this as equation number 3. This m is nothing but your Lipschitz constant. Okay, so now using the definition of phi 2 and phi 1 now. This is the definition of phi 1 and phi 2. Similarly, I will use the definition of phi 2 and phi 1. So I can write phi 2 of x minus phi 1 of x is equal to integral x naught to x into f of t comma phi 1 of t minus f of t comma phi naught of t into dt. So apply modulus to this, you will get mod phi 2 of x minus phi 1 of x. To the right hand side, I will express this in modulus form, then I will divide that modulus so that you will get inequality here. So integral x naught to x mod f of t comma f1 of t minus f of t comma phi naught of t into mod dt. Okay, so we are just splitting our modulus. So now since our function f of x comma y satisfies Lipschitz condition, I can rewrite this whole term as mod phi 2 of x minus phi 1 of x is less than or equal to some k into integral x naught to x mod phi 1 of t minus phi naught of t into dt, right? So now using your equation inequality 3, we can write it as mod phi 2 of x minus phi 1 of x is less than or equal to k into this whole term is nothing but I can replace this whole term by k into m modulus of x naught to x mod t minus x naught into dt, right? So now we know that x1 is less than or equal to x naught, or in general I can say that if x is greater than or equal to x naught, then we can write mod phi 2 of x minus phi 1 of x is less than or equal to k into m integral x naught to x t minus x naught into dt, right? So this is nothing but you will get this as this whole thing will be equal to k into m, integrate this part, you will get x minus x naught whole square by 2. So using the concept of successive approximation, if you continue this process, since we are using the induction process, you will get mod phi p of x minus phi p minus 1 of x is less than or equal to m into k power p by k into x minus x naught power p by p factorial. Okay, so since we are using the successive approximation concept, you will get this. I will call this as equation number 4. So the process of mathematical induction is nothing but we will prove for p is equal to 1, p is equal to 2. So p is equal to 1, you will get here as 0, that is initially we have considered this part, right? When p is equal to 2, this is what you will get. So you can say that the equation number 4 or inequality 4 is true for p is equal to m. Then you will prove the same process is true for p is equal to m plus 1, right? So again, from definition of phi m plus 1 and phi m, I can write it as phi m plus 1 of x minus phi m of x is equal to integral x naught to x f of t comma phi m of t minus f of t comma phi m minus 1 of t into dt. Now using the definition of Lipschitz condition, you can write this. So since m plus 1 is equal to p, I can write this as mod phi p of x minus phi p minus 1 of x is less than or equal to m by k into k power p into x minus x naught power p by p factorial. So this means that the series or the whole sequence phi k of x is a convergent sequence, right, as k tends to infinity. So the first step is over. Now the second step is we have to prove that so in step 2, to prove that phi is a solution to the initial value problem, we have to prove that phi is continuous first. Okay, so to prove phi is continuous, here I have considered 2 points, that is x1 and x2. This x1 x2 belongs to your interval I. So from the definition we can write that modulus of phi k plus 1 of x1 minus phi k plus 1 of x2 is equal to this thing. Okay, I have just applied the modulus and split my modulus here. So here we got the inequality sign. So since we know that our modulus f of t comma phi k of t is less than or equal to m, from this I can write that my LHS part is less than or equal to m into mod x1 minus x2. So here this part we have already proved that phi k converges to phi as k tends to infinity. So from that I can say that phi of x2 converges to phi of x1 as x2 converges to x1, right? So this whole, first what I can say that this whole part converges to 0 as x1 and x2 converges to 0. So from that I can write that phi of x2 converges to phi of x1 as x2 converges to x1. So from the definition of continuity, from this we can say that phi is continuous. So now the step 3 is, in step 3 I have to estimate mod phi minus phi k. I have to find out that what is this mod phi minus phi k. For that I have considered from your theorem statement phi is equal to phi naught plus summation p is equal to 1 to infinity phi p minus 1. This is nothing but your sum of infinite series, right? And this is, we already know that phi k, I can represent phi k in this form. So from this mod phi minus phi k is nothing but just I have substituted the values, I have applied modulus and splitting the modulus you will get inequality here. Using the Lipschitz condition, I can write this as m by k summation p is equal to k plus 1 to infinity k into alpha. This alpha is nothing but x minus x naught whole power p by p factorial. Okay, so if I start p from 0, you will get k into alpha whole power k plus 1 by k plus 1 factorial into this term. So this is nothing but binomial expansion of exponential function, right? So I have just written that here. So as I told, alpha is nothing but x minus x naught. Here I have written alpha is equal to x minus x naught. For simplicity, I have written this whole term as epsilon k. So this whole term epsilon k tends to 0 as the value of k tends to infinity, right? So from this I can say that your LHS part is equal to m by k into epsilon k into e power k into alpha. So now we have find out the value of, we have estimated that mod f phi minus phi k. So next what I will do is, I will say that this phi is a solution to my initial value problem. For that, from your statement I have taken this equation. Okay, so since f is continuous, we can write capital F of t is equal to this function, and this function is continuous on interval I. Okay, so from this you can write phi k plus 1 is equal to successive approximation, so y naught plus integral over x naught to x f of t comma phi k of t into dt. We have already proved that phi k plus 1 of x converges to phi as k tends to infinity. Now I have to prove this equation star. To prove this equation star, I have to prove that this part converges to this part. Okay, so now let's see how we can prove that. I have just considered that modulus of integral x naught to x f of t comma phi of t dt minus, this is for phi k of t. So if you split the modularity, this whole term will be less than or equal to this, right? So now using Lipschitz condition, we can write this whole term is less than or equal to some Lipschitz constant into this term. Since our function f satisfies Lipschitz condition, I can write that this whole term, my LHS part will be equal to k into, this is nothing but epsilon k m by k epsilon k e power k alpha into mod x minus x naught. Now this whole term tends to 0 as your k tends to infinity, right? So that means phi is a solution to the initial value problem, that is y dash is equal to f of x comma y and y of x naught is equal to y naught. So the first main part, that is existence of solution, is over. Now I have to prove that the solution is unique, right? So to prove uniqueness, what I have done is I have considered two solutions. So I should prove that these two solutions are equal, right? For that we know that phi of x, from that I have written what is psi of x. So I have considered modulus of phi of x minus psi of x, just substitute the values, and if you split the modulus you will get inequality. So we know that this whole thing is less than or equal to k into integral over x naught to x mod phi of t minus I of t into dt, right? So now I have considered one function e of x for simplicity. So e of x is equal to integral x naught to x phi of t minus xi of t dt. This whole term is nothing but e of x now. So from this, what is e dash of x? If you differentiate this, you will get mod phi of t minus xi of t, right? So now from this you will get, if you substitute these two things here, so your LHS part is nothing but e dash of x. So I have just transferred my right hand side to the left hand side. So you will get e dash of x minus k into e of x is less than or equal to 0. Okay. So now multiply e power minus k into x minus x naught on both sides of your inequality. So you will get this. This part is nothing but, if you differentiate this with respect to x, you will get this part. You can try that. So this whole thing is less than or equal to 0. Now integrate this, you will get e power minus k into x minus x naught into e of x is less than or equal to some constant. I have mentioned that as constant itself. So from this we have e of x is less than or equal to 0, right? So if you differentiate this, obviously since in the RHS part you have a constant value, so e dash of x is equal to 0. So e dash of x is nothing but mod phi of t minus xi of t. That means you will get mod phi of t minus xi of t is equal to 0. This is nothing but phi of t is equal to xi of t. So we have initially we considered two solutions, and these two solutions are equal, means your phi is unique. So this is all about unique existence and uniqueness of first order differential equation. Thank you.